Purpose of this video is to help you learn how to use the Jet 10 aircraft modeling and analysis software by demonstrating how to use the software to optimize an aircraft for a particular design mission. The aircraft we're going to optimize is a two-seat F-16, and you can see it modeled here, the geometry modeled here on the left, and the aerodynamic analysis results here and the weight analysis results here in the center of the screen. The particular mission that we're going to optimize it for is a training mission to help prepare future pilots of fifth generation fighters like the F-35 and F-22 to fulfill that role. There are no two-seater F-22s or F-35s, so pilots who are going to fly them have to develop their G tolerance, and you learn to use things like night vision goggles and complex systems in a two-seater airplane for safety reasons. That second pilot in the aircraft is there if a student has a loss of consciousness due to pulling heavy G's, then the safety pilot's there to keep everything safe. Likewise, using night vision goggles, the safety pilot's there because night vision goggles restrict visibility of the pilot. And so the safety pilot's there to keep things safe. You can do some of that in a simulator, but you can't develop G tolerance in a sim, and some of the other things lend themselves very well to a two-seat trainer. This aircraft will also replace the T-38, the current supersonic two-seat trainer used by the Air Force. We get our requirements for this mission from a notional request for proposals for the TX, this advanced pilot training aircraft. This RFP was constructed using the requirements in the real TX program, and so these are representative of what the actual contractors are designing to. We have taken all of these requirements and put them into Jet. Over here we have all the constraints. Notice that the hardest constraint, this red line, is this 6.5 G turn, and notice in the mission analysis they have to do 5 720 degree turns for a total of 3,600 degrees, and that takes almost 5 minutes to do that. And all that time they're at full power in afterburner, if there is an afterburner, or nearly so full power to sustain those high G's. The mission is only a 90 nautical mile mission radius, and we've got that modeled in Jet as well. And there's no requirement to go to really high altitudes, and so the minimum altitude for all the combat is 15,000 feet, and so that's where we've modeled it. The 6.5 G turns do allow minus 200 feet per second loss of energy during the turns, but if you do that you have to go up to 18,000 feet to start the turns. So for the mission analysis we're staying at 15,000 because that's conservative. If we bumped all this up to 18,000 feet, we'd find that it burns even less gas, and so that's why we're modeling it at 15,000 feet. The ideal situation would be to fly at 18,000 feet, be able to sustain that 6.5 G turn with no negative piece of S, and then stay right at 18,000 feet for the entire mission. And that'd be better for fuel burn. But if we design and optimize the airplane for the lower altitude, it should be able to fly the higher altitude version of the mission. Alright, so let's get started. We notice right off the bat that this airplane is overpowered for the requirements that are specified. And so we want to go to a smaller engine. Now the first choice for that might be an F404. F404 is the engine used in the F-18. The F-18 has two of those engines, but one of those engines would be available commercially off the shelf and would allow the aircraft to still meet all the design requirements. So we model that by putting in the appropriate maximum thrust. Thrust-specific fuel consumption is very similar. And at this point we say, yeah, we still have plenty of engine. But notice what a huge gain that gave us in terms of weight. It's a smaller, lighter engine. We can reduce the weight of the aircraft commensurately. Also, the smaller engine burns less gas on the mission, so we can drop the weight at least to 21.8. And we're still 21.2. Alright, so we're still overpowered. So let's explore a smaller power plant. There are some out there that could be used. And let's make this easy. We're going to make this equal to 17,700 divided by 11,000 times the actual value that we put in this cell here. Therefore, right now we're modeling the F404, but as we reduce the military thrust, we'll model smaller engines. Now it looks like we can come down to maybe 6,000 pounds of military thrust. Not quite. Let's see what if we can gain some of that back, though. We've got we saved a lot of weight again. We can drop 3,000 pounds. Let's try 17,000. Let's try, oh, that's really close, 17,500. And we've got a pretty good aircraft, except it says we can't do 0.9 Mach and 15,000 feet. That's because we modeled the turns at 0.85 Mach, which is all that's required. So let's change this to 0.85 for now. And in the mission analysis, there is a requirement to do an instantaneous turn at 0.9 Mach, but beyond that, 0.85 is adequate for all the sustained turns. Alright, well, so once again we're a little heavy on fuel, 17,300, and just a little bit more than that, 17,337, oh, 17,045, let's go, 1,345, there we go. Alright. Now this is a pretty nice design at this point, but we can still save a lot of weight. This rear fuselage, the F-16, was sized for the F-100, which is a larger diameter engine. And so we could narrow down the rear fuselage of the F-16 and save quite a bit of weight. Let's go to 6 feet wide. Save 500 pounds. We're down at 16.8 about. And let's try 5.5. Alright, well, this is really a pretty nice solution here. We have a solution to the sizing equation as well. And so at this point it may be appropriate to see if we can optimize this wing a little bit. We've got, as I say, a pretty well converged solution at a fairly small engine size. Let's see if we can help it by changing the wing. Now the wing right now is swept 40 degrees, and that's primarily because the F-16 needs to go supersonic, it needs to maneuver at 0.9 Mach, and that's what it was optimized for. And we can drop the design Mach for this mission because there's no requirement to go supersonic for this TX RFP. Let's try 30 degrees a sweep and see if that helped us. Well, we're a little hard pressed on the 0.95 maximum Mach, but it really helped us a lot on the turn. And it looks like now we have a wing that's too big. So let's try 250. Let's try dropping our weight to 16.2. And let's try 16,000 pounds. Alright, and the sizing equation is saying we can go even smaller than that. Well, at this point, the airplane looks just a little odd. It's a little long, it's a little bit, the horizontal tail's too big. Those horizontal tails should be closer to a third the size of the main wing. Let's drop the horizontal tail size down to 80. And let's shorten the fuselage a bit. I think we can safely do that. Let's go to, let's see, these two here are just numbers typed in. So let's go 42 and 42.5 here, and then let's shorten the fuselage to 43. That seems reasonable. We save some more weight. We're down to 15,400 and actually 15,300. And chances are we could have a smaller engine than we are. Let's try 5,500. Alright, we once again have a positive solution to the sizing equation, and we have a slightly unstable airplane because we reduced the wing sweep. Maybe that's okay for maneuvering. Let's go ahead and fix it for now. Let's try 19 feet. Yeah, very slightly stable, probably better. Let's reduce the sweep of the strake a little bit so that the rear end of the strake lines up better. Let's try 73 with the leading edge of the wing. Alright, well, a little was good. Let's try a little bit less sweep. Let's try 25. And once again, 25 dropped the mission fuel burn. It lets us go to 14,900 pounds. And that's pretty close. We're really having trouble making that maximum Mach at this point. So let's guess that the wing is a little too big. Again, let's try 220. And now we're making the max Mach. We're kind of sitting right in the armpit, if you will, of the two constraints, the max Mach constraint and the sustained turn constraint. And that's kind of where we want to be. I think in the end we'll probably increase the engine size in order to sustain that turn, but for right now let's use this for our optimization. One last thing we should do is move the vertical tail forward before we optimize. It's sticking back there a little too far. Let's try 35 because we shortened the fuselage. And CN beta is still too large. Let's try 34. Okay, and CN beta is still quite a bit too large. Let's try 50 on the vertical tail size. And let's try 40. Let's try 45. Okay, and that's probably a reasonable size and shaped aircraft. Once again, now we're not making the max Mach though, and we can try a little smaller wing area, but I think at this point perhaps we need to go back up in size on the engine. There we go. Alright, well, so we have a solution to the sizing equation that's positive. It's actually quite low. It should give us plenty of margin to have lots of reasonable sizing results as we iterate on the parameters of the wing Notice that now our vertical tail is too small. Let's try 50. The reason it got too small is because the CG moved aft when we made the big engine larger. Alright, so that's good. 47, I guess, on the vertical tail. 46. And we've got a reasonable result. Alright, the last thing we have to do before we run optimization is we need to change what design point is used for mission analysis. Right now, mission analysis is done using the actual values. But when we're going to do wing optimization, we have to optimize, we have to do the mission analysis with the optimum design point. So we handle that by typing equals and click on the desired rather than the optimum. Notice that this significantly reduced fuel burn when we did that, and likewise the desired thrust to weight ratio. And now we're modeling whatever optimum design point the constraint analysis gives us. Alright, let's jump to sizing and optimization. We had 25 degrees of sweep and an aspect ratio of 3. So let's try a range around that, 2.6 to 3.5 and 23 to 27 on the sweep. We've got the taper ratio, the thickness to chord ratio, and the camber already put in. So let's hit the calculate button and see what we get. Alright, we have a true minimum here, it looks like. We have some really high numbers like that one. If we wanted to, we could zoom in on this result by just deleting those big numbers that occurred in just a couple of the runs. Let's see the other big number. Is it this one? Oh no, here it is. And that lets us see our results better. Maybe we can change the maximum here to just 20,000. And now we've got a nice looking plot. And we notice that aspect ratio 2.7 here, and a sweep angle of 24 degrees gives us our optimum wing shape. So let's go try that. Let's try 24 degrees. Let's try aspect ratio of 2.7. Okay, and looks to me like we're not making the max Mach requirement at all now with that 2.7. So part of the reason though is probably because our wing's too big again. So let's try 200. And let's see, the airplane weighs too much. We're burning. Let's go down to 14.2. Yeah, let's try 14,200. And just doesn't seem like it's making the max Mach the way it should. 14.3. Alright. Wing area is still too big. We could try 180. But eventually we're going to have trouble making the turn. So 2.7, maybe let's go back to aspect ratio 3. Aspect ratio 3 seemed to work better, and it's only a couple hundred pounds more. Alright, and maybe a little less than 2.9, but not 2.7. Yeah, 2.9 made it burn more gas. Let's stick with 3. I think everything looks better with an aspect ratio of 3. We still we probably are a little light, short on wing area. That looks better. Let's try 190. Okay. And then let's increase the thrust just a little bit, 6,500, to give ourselves a little bit of a margin. We got to go to about 15,000 pounds. And very good. Notice that the sizing equation is now giving us the same result as our actual within just a couple hundred pounds. So it might be worth running optimization one more time, but I think we've got a really good wing plan for him. I think we've got a well optimized airplane. This smaller engine is actually, there's a F-125 out there that could fill this role. The engine is used in a fighter aircraft produced by Taiwan and also in the X-47. So it's an engine that is available and produces about the right amount of thrust and would give us a very efficient and effective airplane.